Today we're going to continue working with probabilities and look at solving some probability problems. You might call this the miscellaneous probability day, where we kind of hit all those little miscellaneous probability topics that we haven't hit yet. We do have one more major topic we're going to hit, and that's tomorrow's video, but today we'll set that up quite nicely. The first one we're going to take a look at is the expected value. And this is the expected gain or loss. The classic example is, if you play the lottery, will you win or lose, and how much on average in the long run? Or the more applicable place in the business world, insurance salesman selling an insurance policy for such and such a price, and how much will it cost the insurance company or make the insurance company in the long run? And the way the expected value works, we're going to kind of base it on an example, real simple game here that I'm going to offer to play with you. We're going to roll a die, and here's the plan. If it is even, you will pay me the value of the die. So if you roll a 4, you pay me $4. If it is odd, you will receive the value of the die. So if you roll a 5, I pay you $5. Since there's a split between even numbers and odd numbers, it seems like this would be a relatively fair game. You're going to win just about as often as you're going to lose, right? Well, let's look at it. 1/6 of the time, that's the probability, of rolling a 1, you're going to earn $1. Which means, on average, you're going to be earning about 17 cents per game, on average, out of 1s. That's 1/6 times 1. Of course, if you roll a 2, you lose it, and that happens 1/6 of the time also. You lose 2, and I'll show the loss with a -2. 1/6 times -2, on average, you're losing 33 cents per game on 2s. But when you roll a 3, you win 3, and that happens 1/6 of the time. So on average, you're winning 1/6 times 3, 50 cents. But that's going to be offset because 1/6 of the time you're going to roll a 4 and you're going to lose 4. Again, we show that loss with a negative. 1/6 times -4 is -0.67 when we round to the nearest penny on all of these. But when you roll a 5, you win. So 1/6 times 5. And that's going to give you 0.83 as your winnings, on average, out of 5s. And from the 6s, 1/6 times -6, because you're losing, that's going to be a -$1 on average from 6s. So if we want to find out the average result of this game, we can combine all of these together. And so I grab my calculator and we type in 0.17 minus 0.33 plus 0.5 minus 0.67 plus 0.83 minus 1. We find out on average you are losing 50 cents per game. What this is saying is, if you play this game a lot over the long term, you will end up with an average loss of 50 cents per game. You will come out behind. So if you play this game 10 times, you would expect to lose $5. But you're one roll away from breaking even. But that'll only happen 1/6 of the time. In the long run, if you play this 100 times, you will lose $50. 50 cents per game you will lose on average. This is the idea of an expected value, calculating how much you expect to win or lose on average in the long run. And the formula to calculate the expected value, it's not so much a written out formula as more of a sentence formula. What we're going to do is we're going to find the sum of all the products' probability times the payoff. Just like we did with the dice, we multiplied 1/6 times 1, 1/6 times -2, 1/6 times 3. We took all the probabilities times all the payoffs. And notice those payoffs are negative when they're a disadvantage and positive when they are in an advantage. And this is really similar, in fact exactly the same, to the process we use to find a weighted average. For example, if we had a town that had 5% of households owning one TV, 35% own 2 TVs, 45% own 3 TVs, and 15% own 4 TVs, we could find the expected number of TVs in a random household. In other words, what is the average number of TVs? A random family selected, we count their TVs. What could we expect to happen? Well, the way we calculate that expected value is we take the probability times the payoff, or the number. So the first probability, 5% own 1. So that's 0.05 times 1. Probability times the payoff, the number of TVs. 35% own 2, so we'll add 0.35, the probability, times the payoff of 2 TVs. 45% own 3, so the probability of 0.45 times the payoff of 3. And finally, the 15% own 4, so we'll add the probability, 15%, 0.15, times the 4. And then we can grab our handy calculator to calculate 0.05 times 1, plus 0.35 times 2, plus 0.45 times 3, plus 0.15 times 4. And we find out the average household in this town seems to have about 2.7 TVs. So 3 wouldn't surprise us, 2 would be less likely, but probably closer to 3, more likely to get 3, but we might end up with 2 in a random house, 2.7 TVs per household. This is how they calculate values like the average household has 2.4 children. We don't have 4/10 of a child somewhere living. We just have this weighted average calculated in this way. Now I mentioned this is useful in the business world for things like insurance. Let's say a car insurance policy we'll clarify, a car insurance policy costs $700. If a certain accident, or a certain claim I should say, has a probability of 7% and will pay $8,500, how much will the company make or lose But I'll give you a hint. The insurance company never loses on the policy. This is exactly the process that they go through to determine your policy price. They look at all the probabilities and figure out, gee, there's this % chance that I'm going to pay out this much. There's this % chance that I'm going to pay out this much. So in order to cover our costs and make a profit, we need to charge this much. It would seem that if I pay $700 for a policy and the company pays me $8,500, I've come out ahead. Has the insurance policy really come out behind, though? Remember, they sell thousands and thousands, possibly millions of insurance policies. On average, what's happening to their policies? Here, there's something to remember, that the insurance policy is going to cost $700. That cost is paid out whether or not a claim is filed. So the insurance company is going to bring in $700 regardless. So one possibility is the insurance company brings in the $700 and we're going to say no claim. And there's no claim. That means the insurance company, that's the perspective we're taking, how much does the company make, not the customer. The insurance company brings in $700 and the probability this happens, well, if there's 7% chance of an accident or a claim, then the opposite, there's 0.93, is the probability that no claim is filed. We're going to add to that the probability that a claim is filed. The probability of a claim is 0.07. What is the payout? Now be careful here. A common error a lot of students do is they'll put $8,500 in here. The company's out $8,500, but remember they still brought in the $700 policy. But the customer had to pay $700 to the company at the beginning of the year. That's going to give us $7,800 that's actually coming out of the insurance company's pocket. So we're going to call it negative because it's a loss of $7,800. So a 93% chance that they're going to have to pay, that they're going to bring in $700. A 7% chance they're going to pay out a net $7,800. Grabbing the calculator then, 700 times 0.93 plus 0.07 times negative 7,800, making sure your loss is negative. This is going to give us $105. The company is going to make $105 per policy. So if they do this 1,000,000 times, they've got $10 million, and they can easily afford to pay out those few accidents that happen 7% of the time. That is the way expected value is used so the business can guarantee to make money even though they are paying out much more than the policy cost. Because on average, more people are not filing claims. It sets off the cost of those that file a claim. So that's expected value. Multiply the probability times the payoff, add them all up, and that tells you the expected gain or loss on a poker game, on an insurance policy, or on some weighted average. Another thing I want to look at, just really briefly, is how we can use tree diagrams to solve some probability problems that are a little bit more involved than we've seen before, but the tree diagrams actually help us organize the information we need. On my keychain, I have 6 keys, 6 house keys. I have a rental business in town, and I manage 6 properties. But I really can't keep track of which key goes to which property. So I bring all 6 keys every time I go to a property, and I just try one. If that doesn't work, I try the next one. And I keep going until I get one that does work. I want to know what is the probability I can open the door in at most 6 tries. Whoops, nope, there's 6 keys. Haha. Let's go 4 tries. And this is not going to be your classic tree diagram in the sense that, every branch is symmetrical. Because once I get into the house, I'm going to stop trying keys. So I've got this first branch where I either get in or I'm stuck out. The probability that I get in right away is if I get that one correct key out of the 6. If I'm stuck out, probability there is 5 out of 6. I'm going to have to try again. And I will either get in or I will get stuck out. At this point, there are now 5 keys left to try, so I've got a 1 in 5 chance of getting it correct, and a 4 in 5 chance of getting it wrong. If I'm out, though, I'm going to try again. I'll either get in or I'll be stuck out. At this point, there's only 4 keys left, so I've got a 1 in 4 chance of getting it correct, and a 3 in 4 chance of getting it wrong. If I'm stuck out, I will try again. We said at most 4 tries, so that's what we see here is 4 branches. And I'll either get in on the 4th try or I'll be stuck out on the 4th try. With only 3 keys left, there's a 1 in 3 chance I get in, and a 2 in 3 chance I'm still stuck out. This tree helps me organize all my probabilities, especially as they're changing. These are very conditional probabilities. Now we can go down a branch to figure out each branch's probability. In on the first try, that's 1/6. In on the second try, that's 5/6 times 1/5. In on the third try, that's 5/6 times 4/5 times 1/4. 5/6 times 4/5 times 1/4. In on the third try, going down the branch, 5/6 times 4/6 times 3/4 times 1/3. 5/6 times 4/5 times 3/4 times 1/3. Or being locked out entirely is 5/6 times 4/6 times 3/4 times 2/3. 5/6 times 4/5 times 3/4 times 2/3. And now we can multiply these out on the calculator to find out what each probability is. And what's interesting about these is the first probability, 1 divided by 6, is 0.1667. The second probabilities, you might notice the 5's divide out, so we have 1/6, which is also 0.1667. Getting in on the third tries, you'll notice the 5's divide out and the 4's divide out, so we have 1/6, which is 0.1667. The third, you'll notice the 5's divide out, the 4's divide out, the 3's divide out, and we're left with 1/6. So that's, 0.1667 again. And then you'll see the 5's divide out, the 4's divide out, the 3's divide out. We're left with 2/6, which is 1/3, 0.3333. If you don't have anything dividing out, that's okay. Just multiply it out on your calculator. Even if you don't notice they divide out, multiply it out on your calculator, and it'll come out just fine. I want to get in, I want the door open in 4 tries, at most. So 1 try, 2 tries, 3 tries, 4 tries. I don't care about the getting stuck out part. We just need to add these together. 0.1667 plus 0.1667 plus 0.1667 plus 0.1667. That's going to be 0.6667. Actually 8 because of a round off error. But that's okay. We're within 1,000th. That's reasonably close. Within a round off error. So the probability I get in at most 4 tries is 0.6668. About 2/3 of a chance that I get in at most 4 tries. The tree diagram really helped me visualize how many keys were left. There were 6 keys, then there were 5 keys, then there were 4 keys, then there were 3 keys, and that really helped me see and adjust my conditional probabilities. Let's look at another example. Let's say a jar has 4 red and 2 green marbles. Another jar has 3 red and 1 green marble. A jar is chosen at random and a marble is drawn. What is the probability a green marble is drawn? Now we can't just pool these together and say, well, there's 7 red and 3 green, so there's a 3 in 7 chance. I'm sorry, a 3 in 10 chance, or a 30% chance. That's not going to work, because if I were to select the first jar, I'm much more likely to end up with a green. If I were to select the second jar, I'm less likely to end up with a green. So the jar I pick is going to directly affect and change the probabilities. So to help us organize this, we're going to set up a tree where we look at either picking jar 1 or we look at picking jar 2. Now we assume these jars are completely identical. There's no way one would be chosen over the other, so we're going to say there's a 1 out of 2 chance that each jar gets picked. Pretty much there's a 50-50 chance. Once I pick that jar, I could either end up with a red or I could end up with a green. If I were to pick jar 1, there are 4 reds, so I have a 4 out of 6 chance of ending up with a red. There's also 2 greens, so I have a 2 out of 6 chance of ending up with a green. Versus if I had picked jar 2, I could have ended up with a red or a green. The probabilities are just different now. In jar 2, there are 3 reds out of the 4 and 1 green out of the 4. So to calculate my probabilities, we multiply down the line. I could end up with a red. That's a 1/2 times 4/6 chance. Doing that on the calculator. 1 divided by 2 times 4 divided by 6. That's a 0.3333 probability. I could end up with a green. That's 1/2 times 2/6. That's going to be a 0.1667 probability. Or I could end up with a red going down the branches. That's 1/2 times 3/4. 1 divided by 2 times 3 divided by 4 is 0.375. I'll put a 0 on just so we have the same number of decimal places. Or I could end up with a green. That's 1/2 times 1/4, which gives us 1/8, or 0.1250. And we want to end up with a green marble. So let's combine and add the green marbles together. When we add, we got 0.1667 plus 0.1250. That gives me a probability that I get a green is equal to 0.2917. I want to notice that's different than what we expected. I'm kind of off the screen here. What we expected is there were 3 greens out of the 10 marbles. We would have expected a 30% chance, but actually it's a little bit less than 30% chance. The probability I get a green is actually 0.2917. The tree diagram can really help me visualize and see the difference when these probabilities are conditional on something like what happens in the first decision, because that's going to affect and change the probabilities. This is what you're going to get a chance to look at on the homework assignment today, is using tree diagrams to help you organize these conditional probabilities and also some expected values. Tomorrow we're going to look at how these tree diagrams and adding the correct parts of these tree diagrams can help us calculate some more difficult conditional probabilities. But for now, take a look at your homework assignment, and we will see you tomorrow. Come with questions.